Hi, my name is Rohan Aluri, and this is my Motion of a Falling Object lab. Some of the intended goals of this lab were to analyze the various positions of an object moving under free fall through the use of the tracker software in order to create an experimental model of the object's motion, to create a computational model that resembles an object moving under free fall through Newton's second law in the GlowScript software using the force of drag, to create an additional model using only the force of gravity, and to observe the three graphs and explain the key differences and why we are interested in the lab's implications. We may be interested due to the concepts of gravity and drag and how we can manipulate these forces in order to change the free fall of an object. Some of the physics concepts that were involved in this lab were Newton's second law, the force of drag, and the force of gravity, where terminal velocity can occur when the force of gravity is equal to air resistance. In order to avoid poor quality, I will be displaying a recorded version of my tracker software, where in the bottom right you can see all the individual times and the movement in the y direction, where in the top right you can see a graph of this change, which is negative and is curved, and to the left you can see the actual falling object of this paper bowl and all the individual points that were tracked as it fell to the ground. Over here you can see the same exact graph that was plotted, that was negative and it was curved. Both concepts of gravity and drag are applied as well. This is my computational data via GlowScript and the code that I used. Some key things to take away is that the mass of the ball was 0.001 kilograms, that gravity was 9.8, that the B value was 0.0322 considering drag and gravity, but is only 0 when considering only gravity, and the time it took for all this to occur throughout the code. On the left, you can see the graphs that GlowScript presented considering drag force and not considering drag force. The key takeaways is the shapes of the graphs. As you can see, there's a y asymptote in the velocity versus time graph considering drag force, and there's a negative and linear slope when not considering the drag force. The computational model with only the force of gravity seems to be negative and curved because only gravity due to the Earth is present, which is negative 9.8 meters per second squared. That's why there is a curved slope that is in the negative direction. For the computational model with the force of gravity and the force of drag, you see a more fairly linear slope that is still negative because gravity in the negative direction and drag in the positive direction are eventually going to cancel each other out. However, this does not always happen, resulting in a fairly linear and negative slope. When considering all three slopes together, we can see that free fall is composed of drag in the positive y direction and gravity in the negative y direction. Drag and gravity have equal magnitudes. When drag and gravity have equal magnitudes, this results in no net force. The experimental and computational model with drag and gravity are almost identical as seen by the overlap here. This shows how in real life, the gravity and drag both have an effect on an object. Without drag, it can be seen that objects accelerate much faster. Some potential sources of error within this lab was that I misclicked the center of the object in tracker, that I did not drop the object from rest, that wind currents came from the AC, and there was movement of the paper bowl in the X and Z directions. When considering additional questions, the computational model that considers both the force of gravity and the force of drag predicts the terminal velocity. This is because the initial position time graph has an asymptote along the y-axis, which can be seen as well on the velocity versus time graph provided in GlowScript. As both the forces acting upwards and downwards are balanced at terminal velocity, the forces in the y direction are at equilibrium and the net force would be 0. Similarly, the value for terminal velocity wouldn't change if there was an initial velocity on the object being thrown rather than dropped. This is because the terminal velocity can only be achieved when the object's acceleration is equal to 0, so there is no change in velocity considered. Any object thrown at any velocity will eventually slow down to its optimum terminal velocity. When I changed the initial velocity in the computer models, the terminal velocity maintained the same value as when the initial velocity was 0. In conclusion, after completing the lab, I believe that I have received further insight regarding the underlying relationships between the physics concepts of the force of gravity, terminal velocity, the force of drag, and net force. This can be seen through comparing the different experimental and computational models of my object when manipulating the presence of gravity and drag. If we were to replicate this experiment in a closed system and an object starts perfectly from rest, then we would be further able to accurately describe the motion in free fall. Through the implications of this experiment, additional questions begin to arise as to how would the computational and experimental graphs change if the object used was significantly greater in weight, and to what extent does having no net force on an object mean in a perfect world? Thank you for listening.